Good morning friends, welcome back to Panika Tutorials. In this video, I want to discuss what is the need for multi-level paging, what is a multi-level paging with an example. So I request everyone to watch the complete video for better understanding. First let me discuss what is the need of multi-level paging and what is the issue we will face in single level paging. Okay, let's consider that we have a main memory. Okay, we have a main memory. Usually the main memory is logically divided into frames. Okay, this is frame number 0, frame number 1, frame number 2, so on. So main memory is logically divided into frames. Similarly, we have the process, or even we can call it as a logical address space. We can call the main memory as a physical address space, process as the logical address space. So the process is logically divided into pages. We'll have page number 0, page number 1, page number 2, page number 3, so on. The page size will be equal to frame size. That is the rule. Meaning is that one of the page from a process can be easily fit in one of the frame in main memory. Now, CPU will generate the logical address. Okay, the logical address consists of two parts. One is the page number and another one is page offset. But the particular page is stored in the main memory. So we need to generate the physical address. So who will generate from the logical address? The memory management unit will convert the logical address to physical address. In a physical address, we will have frame number and then frame offset. Okay. The number of bits in a logical address depends on the process size. The number of bits in the physical address depends on the main memory size. And the page offset will depend on the size of a page. And number of bits in a page number will depends on the number of pages. Similarly here, as the physical address consists of frame number and frame offset, the number of bits required for the frame offset will depend on the frame size. The number of bits required for the frame number will depends on the number of frames in the main memory. Is it clear? Now, suppose let's take that CPU is asking for 6th byte in the process P1. Let's take that this is process P1. Now let's consider that 6th byte is there in the page number 1. Okay, 6th byte is there in the page number 1. But this page number 1, let's take that it is kept in the frame number 3. Okay, page number 1 has been loaded in the frame number 3. So, the memory management unit has to convert this logical address to physical address such a way that it will go to the frame number 3 and fetch the information. Is it clear? So, to know that the process which page has been loaded in which frame, we will have a page table. Okay, the purpose of page table is, let me write here, we will have a page table. The page table purpose is that it will have the information of all the pages of the process. So the number of entries will depend on number of pages. Let's consider that in this process we have 10 pages from P0 to P9. Then this page table also will have P0, P1 up to P9. Okay, so the number of entries in the page table will be equal to number of pages in a process. Now let's take that page number 0 has been loaded in frame number 1. Then that information will be there. Okay, frame number 1. And we will have extra information also such as valid bit, then protection bits, and then we will have cache enabled, disabled bits. So I am only worrying about the frame number. Those are optional bits, so I am not worrying it. Is it clear? So the main information will be there in a page table is the frame number. Okay, so let's consider that page number 1 has been loaded in the frame number 2. So that information will be there here. In frame number 2, the page number 1 of the process will be loaded. And remember one important point. Each process has its own page table. Is it clear? Now we need to compute the page table size. Okay, suppose let's take that we have some 16 pages are there. So let's take that we have 16 pages are there. Okay, or 10 pages are there, whatever it is. Let's just consider we are following the 10 pages. So 10 pages are there, and then each page is 4 bytes. Each page entry meaning is that we have the frame number, and then we have the optional bits. All this information is 4 bytes, meaning is the 32-bit information is available in one of the page table entry. See, in page table, each page will have the information. That information will be optional bits and the frame number. The total optional bits and the frame number, let's assume that it is 32-bit, which is 4 bytes. Then page table size will be 40 bytes. Let's consider that usually what will happen is that we need to store this information also somewhere. And where this information will be stored? It should be stored in the main memory. Am I right? So the page table also should store in one of the frame. In one of the frame, we will keep the entire page table, so that whenever CPU want to, means not CPU, memory management unit want to convert the logical address to physical address, first it will go to the page table. Then you can ask me, sir, how the information will come to know by the memory management unit is that the page table is there in, suppose let's take that it is there in the frame number 10. How that information will be available? It will, the CPU will maintain one register. In that register, it will store the base address, meaning is that starting address of the page table. Okay, so it will go to the base address and then get the particular frame information. Is it clear? Are you able to understand? So it will go to the base address, meaning is that starting address, then it need the page number 10 information, then it will go to the particular page and get the frame number, and it will go to the frame number and get the information. Is it clear? Are you able to understand? So ideally the entire page table should be loaded in one of the frame. Let's consider that this entire page table is size is more than the frame size. Then can we keep the entire page table in a single frame? Not possible. Are you able to understand it or not? If the page table size is less than or equal to frame size, we can keep it in one of the frame of main memory. But if the page table size is more than the size of a frame, then it is not practically possible to keep it in one of the frame. Then again what we have to do? We have to make this page table into multiple pages. Is it clear? So again what I will do, if this page table size is more than the frame size, again I will divide this one into multiple pages such as P0, P1, P2. That information I will store in another page table, meaning is that I will create a page table of level 2. Okay, and I will store this information in page number 0. What information will be there? This information. Is it clear? Are you able to understand it or not? So each page table, again if it is size is more than the frame size, again we will divide into multiple pages, and this information we will store it in another page table. So this information will be available in this page table. So this is what the purpose of multi-level paging. If the single page table size is more than the frame size, then we will go for the multi-level paging. If you did not understand this concept, don't worry. I will discuss the multi-level paging with this example. Okay, just remember one thing. If the page table size is more than the frame size, then we will go for the multi-level paging. Okay, and that page table again further divided into various number of pages. That information we will keep it in another page table. Okay, is it clear? Now let me discuss with this example. They have given that physical address space. Okay, physical address space is 256 MB. Okay, 256 MB meaning is that It is 2 power 28 bytes. Okay, and logical address space is 4 GB, meaning is that process size is 4 as 2 power 2. GB means 2 power 30. So we have 2 power 32 bytes. And frame size has given as 4 KB. Okay, 4 KB. So 4 KB means 2 power 2. KB means 2 power 10, which is nothing but 2 power 12 bytes. If the frame size they have given, we can easily find the page size, because the frame size will be always equal to the frame size, which is again 4 KB, which is 2 power 12 bytes. Is it clear? Are you able to understand it or not? Now we will do the multi-level paging with this example. So we have a main memory, okay, which is nothing but the physical address of 256 MB. Okay, main memory is 256 MB and frame size is 4 KB. Then first thing I need to find is that number of frames. Okay, number of frames in the main memory will be depend on main memory size by frame size. Main memory size is 256 MB, which is nothing but 2 power 28 bytes by frame size is 4 KB, which is 2 power 12 bytes. Then if you cancel bytes and bytes, and 2 power 28 by 2 power 12 will be equal to 2 power 16. So you have 2 power 16 frames are there in main memory. Okay, you can write it. Number of frames in is equal to 2 power 16. If you have 2 power 16 frames, number of bits required to represent one frame. To represent a frame. If you have 2 power 16 frames, how many bits are required to represent one frame? You need 16 bits. Is it clear? Are you able to understand? Suppose let's take that you have 4 pages, okay, such as page number 0, page number 1, page number 2, page number 3. Then you need how many bits to represent these 4 pages? 2 bits, such as each bit will have either 0 or 1 information. So it will be 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 is page number 0, 0, 1 page number 1, 1, 0 it is page number 2, 1, 1 page number 3. Is it clear? So this is the binder representation of the decimal number 3. So if you have 4 combinations, you need 2 bits to represent those 4 combinations. Similarly, you have 2 power 16 frames are there. So you need 16 bits to represent one frame. Okay. Now we will divide the logical address space into pages. Okay. Logical address space or the process. They can even call it as a process size, logical address space or virtual address space also. Okay, so it is how much? 4 GB. Okay, look at here, the main memory size is lesser than the process size, so we will use the virtual memory concept to execute this process. Is it clear? Are you able to understand? So if you have 4 GB of a logical address space and the process size, not process size, page size is 4 KB, then we can find the number of pages. Number of pages is equal to logical address space or the process size by page size. Now the logical address space is 4 GB, which is nothing but 2 power 32 bytes by page size is 4 KB, which is 2 power 12 bytes. Bytes and will be cancelled. You will get 2 power 20 pages. So you have 2 power 20 pages. You can write here number of pages is equal to 2 power 20. Okay, if you have 2 power 20 pages are there, starting from 0 to 2 power 20, you will have 0 to 2 power 20 minus 1. Okay, now if you have to maintain the page table for this process, okay, let me keep it as page table PT, okay, page table. Then the number of entries in this page table will be how many? Number of pages in a process. How many pages are there? 2 power 20 pages are there. So even this page table will have the pages from 0 to 2 power 20 minus 1. Okay, are you able to understand it or not? Remember one thing, each page in the page table, what information it will have? It will have the optional fields and also the frame number. The optional fields such as cache enabled, dirty bit, protection bits, all these things. So the optional bits, if you neglect it, you will have the frame number. Am I right or wrong? Suppose page number 0 of the process, let's keep that it is there in the frame number 0. So this information will be there. So that is the purpose of page table. So a particular page of the process has been loaded in which frame, to identify that one, each process has its own page table. Is it clear? Now look at here, frame number 0 is there. How many bits are required to represent any frame? 16 bits are required. So each entry, if you neglect the optional bits, we will have the frame number of 16 bits. 16 bits is nothing but 2 bytes. So each entry size is 2 bytes. Like that, you have 2 power 20 entries are there. Then what is the page table size? Okay, are you able to understand? Each entry size is 2 bytes. Like that, you have 2 power 20 entries. Then page table size is equal to number of pages into entry size. Okay, here the entry size is 2 bytes. So number of pages is 2 power 20 into 2 bytes, which is 2 bytes, which is 2 power 21 bytes, which is nothing but 2 MB. Okay, are you able to understand? So this page table size, let me write here, this page table size is equal to 2 MB. Now what we are keep on saying, this page table ideally should be loaded in one of the frame of main memory. Okay, now look at what is the frame size. Frame size is 4 KB only. In a 4 KB space, can we keep a 2 MB information? Because the page table size is 2 MB. If the page table size is 2 MB, your frame size is 4 KB, can you load 2 MB information in a 4 KB space? It is not practically possible. So meaning is that this entire page table we cannot load in single frame of main memory. So what we have to do? Again, we have to divide this page table into multiple pages. Is it clear? So now again we need to divide it into certain pages. So number of pages in the page table 1, let me keep it as page table 1. Number of pages will be equal to what? The size of this one, page table size, by page size. Is it clear? Are you able to understand? What is the page table size? 2 MB. Means page table size is 2 MB and page size is 4 KB, which is nothing but 2 power 21 by, are you able to understand? 1 MB is 2 power 20 and 2 MB it is 2 power 21 and 4 KB, which is nothing but 2 power 12 bytes. This is also in bytes, this is also in bytes. This bytes and this bytes will be cancelled. You will have 2 power 9 pages. Is it clear? So number of pages in page table 1 will be 2 power 9 pages. Is it clear? So if you have 2 power 9 pages, let me keep it here. This is a page number 0 and this will be 2 power 9 minus 1 page. Are you able to understand 2 power 9 minus 1 page? So this page table 1 is again logically divided into pages. Now that information you should store in some other page table. Am I right or wrong? Look at here. The process is logically divided into pages. That information we are storing in one page table. Now this page table is again further divided into pages. That information we should store somewhere. Am I right or wrong? So we will have a page table 2. Okay. In page table 2, how many entries will be there? Can anyone tell me? If you have 2 power 9 pages of this page table 1, that information we are storing. So how many entries will be there? 2 power 9 entries, or I can say that 2 power 9 informations will be there. Okay. In the page table, we will have entries from 0 to 2 power 9 minus 1. And what is the information will be there in each one? Again, here also frame number only will be there. Am I right or wrong? Are you able to understand? Here also that particular page frame number will be there. So if here also frame number is there, we got 16 bits required for the frame number. So 16 bits are required for the frame number, which is 2 bytes. Then how can we find the page table 2 size? Page table 2 size is equal to number of pages, which is nothing but 2 power 9 pages, and each page has the information of 2 bytes, because I am not considering the optional fields. Is it clear? Are you able to understand? Usually sometimes they even give the entire this size also. That time we no need to count the number of bits required for the frames. Okay, so 2 power 9 into 2 bytes, which is nothing but 2 power 10 bytes, which is 1 KB. Okay, so this page table size is 1 KB. If this page table size is 1 KB, can we load this in one of the frame? Yes, it is possible. How it is possible? The frame size is 4 KB. If frame size is 4 KB, if you have 1 KB information in 4 KB space, can we load 1 KB information? Yes, possible. So this page table 2 can easily fit in one of the frame of main memory. So this information will be there in the main memory. Are you able to understand? So we will do the multi-level paging such a way that that outer page table can easily fit in one of the frame in a main memory. If it fits, then we will stop the process. If it is not fits, again we will divide this page table into multiple pages. That information we will store it in one of the page table. Is it clear? Are you able to understand? So here what we have to do. Now CPU will generate the what address? CPU will always generate the logical address. Okay, are you able to understand? CPU will generate the logical address. The logical address will consist of two information. One is the page number and the next one is page offset. Okay, the number of bits in logical address depends on the logical address space. Here the logical address space is 4 GB, so it will be 2 power 32 bytes. So you have logical address of 32 bits. If logical address is 32 bits, then page offset will depends on page size. Okay, the number of bits required for the page offset will be depend on the page size. Look at the page size. Page size is 4 KB. So number of bits required for the page offset is 12 bits. Then if 12 bits are there, out of 32 bits, 12 bits are occupied for the page offset, then how many bits will be required for the page number? 20. So if you look at here, we will have 2 power 20 pages in the logical address space. That is what we have counted. Number of pages is 2 power 20. But if it is single level paging, it is okay. But this is multi-level paging or two level paging, because we have a page table 1 and page table 2. So we have two level paging. So what we have to do is that this one again will be further divided into two halves. Okay, how we will compute that one, let me discuss somewhere here. I'm identifying the space. Okay, let me erase this one. We already computed the page size, all these things. Okay, let me use this space. Okay, so CPU is generating the logical address of 32-bit. Okay, that will be divided into three offs now. One is the page offset, which is 12 bits. Okay, and page number will be now further divided into two parts. This entire page number size is 20 bits. Okay, now how we will divide this page number into two halves, we will discuss now. Now look at here, the page table 2, how many entries are there? 2 power 9 entries are there. So you should need 9 bits to represent one of the page. Because look at here, whenever the CPU is generating the page number, first it will go to the outer page table. Are you able to understand? So first it will go to this page table. Okay, then it will find the information, then it will come to here, then the frame number will be there, so that frame number will go to the main memory. So this is about the multi-level paging. So CPU first will go to the outer page, whatever the information will be there, it will fetch that information and go to the inner page table. From that inner page table, it will go to the main memory to get the particular information. So the number of bits required will be 9 bits, because we have 2 power 9 pages. If you have 2 power 9 pages, you need 9 bits. Okay, are you able to understand? Now if you look at here, this total size is 20 bits. If this is 9 bits, then this one will be 11 bits. Okay, are you able to understand? Like this you can compute, or if you want to compute in a normal way also, I will discuss for you. Okay, is it clear? Now look at here. If the page table size is 2 MB and you have the, how many pages are there in this one? 2 power 20 information is there, and each entry is how much? 2 bytes. Are you able to understand? If, let me write here, each entry occupies 2 bytes. And what is the page size? Page size is 4 KB. If page size is 4 KB and each entry is 2 bytes, then how many bytes of information can be kept in single page? See, are you able to understand? We have 2 power 20 entries are there. This entries again further divided into pages. Am I right? Page number 0, page number 2 power 20 minus 1. Like that we have divided the pages. Am I right? Are you able to understand? 2 power 9 minus 1, not 2 power 20 minus 1. Page number 0, page number 2, page number 3. Now if you look at here the page offset will tell you what? The entry. Suppose let's take that if I say page offset is 2, then here in each page we will have the information 0th byte, first byte, second byte, like that. So this is about the offset. In that page, what byte you want to fetch? Similarly, if you have a frame number and frame offset, you go to the frame number. Frame offset is that byte from that frame we need to fetch it. Is it clear? Are you able to understand? So if the page size is 4 KB, each entry size is 2 bytes, then number of entries in this one will depend on what? It will depend on page size by entry size. Okay, I hope you are able to follow with me, because this page size is 4 KB. Now each entry is 2 bytes. Now how many entries are possible will be depend on page size by entry size, where the page size is 4 KB, entry size is 2 bytes, then you will have 2K entries are possible. If you have 2k entries, then you need 11 bits to represent that one. So that's why you will have 11 bits here. Are you able to understand? So this is the way the logical address will be split up. Okay, one is the outer page 1. If I consider this is a page table 2, this is the page table 2 information, this is the page table 1 information, and this is the page offset. So this is the way we can go for the multi-level paging, and this is an example for two-level paging. I hope it is very clear for you. If you have any doubts related to this concept, feel free to ask me in the comment section. I will try to clear your doubts as early as possible. In the next video, I will take few more examples and solve it for you. If you still have any doubts, I request you to go and watch the next video for better understanding. Thank you for watching the complete video. Have a nice day.